Good afternoon. So let's get started at 6:15. Let me start it. Mhm. So good evening. I am Abhinav Chandrakar. I am the PA for this course, Mechanical Behavior of Material, being hosted on NPTEL, and it is taught by Professor Sankran from IIT Madras. Today we'll have a extra doubt and problem solving session. Already we have previously completed 12 sessions for the 12 weeks contents. Today we'll have the last one where we'll try to solve one more assignment which covers all of the topics, and as well um, take some more doubts if there are any. So also let me just check if there are any doubts on the discussion forum. Mm. There's nothing on the discussion forum. So let's do one thing. There was some content of week 12 which was left previously. I think around one lecture. So we'll do that. We'll solve some of the questions of week 12's assignment of 2023 which were left. I think two questions were left. So we'll solve them, and then we'll look at assignment 0, which covers uh, all 12-week contents questions. I think that will take up 2 hours of our time. So let's get started. Hmm. We look at some of the concepts of week 12. It's more of a summarization and covering some of uh, the fatigue related aspects for non-ductile materials or non-metallic materials, those which might be crystalline or semi-crystalline or polymerase. Yeah. So previously we had seen some summarization of fatigue, majorly the Coffin-Mansion equation, Baskin equation. These are relations which are very commonly used, and these are simple relations, so they can be very easily applied to get some estimated relationships or for analyzing your fatigue test results. These are useful. And then we have Paris law, which connects your fracture mechanics to fatigue for studying fatigue crack growth phenomena. Now, continuing from there, um, Professor talked about microcracks in materials. So, um, when you are applying fatigue, then due to the dislocation based phenomena which occur, it's possible for microcracks to form. And uh, and professor has shown how the microcrack density will change as you increase the number of fatigue cycles. So basically what happens is that um, tensions opens up these micro cracks and makes formation of new cracks, while compression can close these cracks. So if you have a zero tension, zero load cycle, which means only tension, no compression, then initially the micro crack density in your material will increase with number of cycles. Then it will tend to saturate because you have too many, and then failure mechanisms can start. Hmm. I think this is more applicable for brittle materials or semi-brittle materials because these materials do not have the plasticity to accommodate small strain localization, and that's why formation of microcracks is very easy in such materials. Also, while we know that in ductile materials, cracks or flaw initiation starts at surface almost all the time, but in brittle materials, because your surface is hard and you have flaws inside, for example, these small microcracks which are created during the tension cycles, flaw initiation can happen from these interior microcracks or other flaws, and that can later on lead to failure by crack propagation. So continuing with this, at high temperatures, for these kinds of materials, it is possible that you can have viscous flow along the boundaries, so flow of amorphous phase at the interfaces, which can lead to a cavity or microcrack formation at the interfaces, because interfaces are more amorphous areas and have a higher energy associated. So diffusion is faster there and you have viscous flow at high temperatures. So this is also the same thing. Dislocation pileups are much more easier at semi-brittle solids because their mobility is very low and crack nucleation can occur as a result if the stress localization is too high. Hmm. One way to combat this um, limitation of what we called brittle or semi-brittle solids, majorly ceramics, because ceramics have ionic bonds which can have these issues which we talked about and which have these mechanisms occurring. So one way to deal with it is having phase transformation, which can help in accommodating strain absorbing energy and therefore improving the fatigue life considerably. So we can have transformation induced ceramics. The Very popular example of this is ZNO, which is partially stabilized by magnesium oxide. So we can understand that ZNO by itself will be um, quite brittle because it is a ceramic having oxide bonds. But when MgO is added, it forms the phase which it exists in becomes metastable. So what can happen is that when you apply load, there is stress concentration that can result in phase transformation, which will lead to strain accommodation as well as energy absorption. And this kind of a transformation is called Martensitic transformation. This also happens in ductile metallic materials such as steel. We have transformation induced plasticity in many steels, which is utilized very extensively to improve the toughness of the material. So you can have a high steel, high hardness, high strength steel, which will also be tough due to this kind of trip phenomena. And this can lead to a stable crack propagation, because as the tip propagates at the as the crack propagates at the tip, phase transformation will keep on occurring, which will tend to blunt the tip. So propagation will be slower and more stable. This is also seen as shear band formation in the microstructure due to the shear and volumetric strains which are involved in the phase transformation. In case you have any doubts, you can let me know related to what I'm saying now or some other topic. We can discuss on that. So now we'll look at fatigue in polymers, just very briefly. So in polymers, you have a very different phenomena occurring. We have seen about deformation in polymers earlier. Professor has taught it separately. So in polymers, the deformation majorly occurs not by dislocation, but by molecular rearrangements. So you have chains of molecules uh, which have which can be heavy and long also depending on the polymer, and these molecules are usually um, weakly bonded to each other by hydrogen bonding, and they form certain structure. So when they are being loaded, then these molecular chains can move with respect to each other. The bonds can break, they can rearrange, because it's easy to move the molecular chains since they have very weak bonding with each other. But it is very difficult to break those chains, because then you have covalent bonding within the chain, which is very difficult to break. So in fatigue also, the molecular rearrangements lead to the sample straining, are the reason for the sample straining. And we tend to see in fatigue a formation of trace, which is a kind of a shear band. And sir has shown how this looks. It has a epsilon shaped profile. We'll see later. So these crazes or shear bands form, which uh, are responsible for the strain accommodation, for the straining of the sample. And it is observed that these crays form in tension loading, but in compression they do not form. And in general, we see a softening of polymers when it undergoes fatigue. So initially it will have some strength, but as the number of cycles increases, because of molecular rearrangement, it will become easier to strain them more. So their strength will decrease, softening will be occurring. And because of this craze, they exhibit stable crack growth. Oh. Anything that retards crack growth or blunts the tip of the crack, it can help to prevent very mm, catastrophic growth of crack in any direction. So, in a way, you can say that it is a stable crack growth because it moves slowly and in a and its path is somewhat restricted to a particular direction only. Now coming to fatty crack growth in polymers, here we see epsilon shaped profile when we see the microstructure, and that is due to crace formation. So it's called a shear crace process where shear bands form and then crace forms, and these two keep occurring one after the another, and in this way the crack slowly propagates. So with this, actually fatigue ends. We first concentrated on fatigue crack growth after fracture mechanics. Then we went into some basics of fatigue and concepts related to fatigue, how materials behave under fatigue, what are the microstructural evolutions that occur, and later on we took up some less um, some non-metallic instances also, or non-ductile such as BCC crystal structure materials, and saw how mechanisms and properties differ for them. So with this, week 12 is over. The contents of the course are over. We can move to the assignment now. I think assignment 11 was done, finished. Yeah. In assignment 11, from what I remember, we couldn't get the right answer for question 7, right? Yeah. So I haven't been able to resolve this yet. I'll let you know if I can. So for 7, we were getting slightly different answer. Here, we were getting a very different answer. So I have asked a friend. She'll let you me know in some time. So I'll share that time. In assignment 12 also, we had issues with some answers. This was not matching. So we need, I'll try to see if I can resolve this also. Let's look at question 6 now. A microalloyed steel subjected to two fatigue tests at at 400 and 250 megapascals. Failure occurred after these number of cycles in each. Estimate the fatigue life at 300 megapascal of a part made from this steel, which has already undergone certain number of cycles at 350 megapascal. Okay. So we have been told what is the life for two different number of cycles. We need to find the life if it has undergone a certain kind of loading. Let's see how to approach this. So we can utilize the minus rule to solve this, but we also need to know the total number of cycles to failure, which will occur at each load. Only then you can use minus rule. Like you need the total number of cycles at each load to use minus rule. So how can we estimate the total number of cycles? If we know some equations, maybe we can. Uh, but nothing was mentioned in the question. I feel the question is incomplete. The information is not enough to answer this. Mhm. In my opinion, you need more information to answer. If you have any ideas, you can let me know on how to tackle this. We need the number of cycles at 400, at 300 megapascal and 350 megapascal. The total number of cycles for failure. Um, okay. Or we can estimate it also by using some relations, I think. Let's try. I think we can estimate it. Hmm. So this was question number 6. We can use Baskin's equation here. We have to relate the stresses to the total number of cycles, the stress amplitudes. So let's say you have sigma 1 equal to sigma f n raised to b, nf raised to b. This is Baskin's equation. where 1 corresponds to 400 plus minus 400 MPa loading. Sigma 2 is also, I think here we have to put delta sigma 1 by 2. Let me write it properly. Here this is for plus minus 400 MPa loading. These are Baskin's equations relations. We need to find sigma f and b, right? Let me just double check the equation is right or not. Hmm. Yeah, I think we can do this way. So if we um, first take the ratios, delta sigma 1 by delta sigma 2. So say delta sigma is the amplitude here, that is maximum minus minus the difference between maximum and minimum stresses equal to n1 by n2 raised to b. So 400 by 250 equal to 2 by 1.2 to 10 raised to minus 2 whole raised to b. So b will be ln of 2 by can you unmute your mic? Some noise is there. C into ln of this. Sorry, it will be reciprocal of this. So let me write it again. Equal to ln of 40 by 25, 8 by 5 divided by ln of 2 by 120 equal to, let's calculate and see. We have got B. Now we need sigma F. It's a bit lengthy problem. So sigma F will be equal to, if we do for the case of 400, 400 by N2 is 2 into 10 raised to 4, sorry, N1 2 into 10 raised to 4 raised to B minus 0.1148. This will give us a value of sigma F. So this will be equal to slightly long problem. I hope the screen is visible. It's not, no? Okay, I'll share again. Let me know in case the screen goes off. One two four 6.8.9. Now we need to know what will be the value of NF and N for plus minus 300 as well as N plus for plus minus 350 MPa. So N is equal to delta sigma by 2 by sigma F whole raised to minus B. So N for plus minus 300 megapascal equal to 300 by 1246.9 raised to it should not be minus B, 1 by B, right? One by minus 0.1148. Actually, my battery has become very low. That's why it's switching off. I'll have to plug it in. Yeah, now let's do it. So this is equal to, I hope we haven't made any mistakes. Let's be careful. So the answer is coming out as 2.45 into 10 raised to 5. Okay, this seems reasonable. It's less than the one for 200, but more than the one for 400. So this should be fine. So the 400 and 250, sorry. Now let's similarly try to find out for plus minus 350.
Screen sharing is not enabled.
This is coming out to be equal to 6.4 into 10 raised to 4. So this is less than the one for 10 raised to 4. Sorry, more than the one for 400 megapascal. So this also seems fine. Now we can use the minus rule on it. So we know hmm, that according to minus rule, n1, n at a particular value of sigma, let's say n1 by n, n at n1 for failure plus n2 number of cycles. So number of cycles in load for loading of sigma 1 by number of cycles to failure for sigma 1 plus number of cycles for loading sigma 2 divided by number of cycles to failure for sigma 2 will be equal to 1 as per minus rule. So we just take the ratio with the number of cycles to failure. Now let's try to see. So we know that n1, let's say 1 is for 300 megapascal. Okay, let's say 1 is for 350 megapascal or 300 since we took 300 first, and 2 is for 350 MPa. We need to find the value of um, n1 here, the one for how many number of cycles can it go for can it undergo at 300 megapascal loading if it has already gone through few number of cycles at 350 megapascal. So n1 equal to 1 minus n2 by nf2 n2 nf 1. This will be equal to 1 minus N2 is 2.5 into 10 raised to 4. So 2.5, 10 raised to 4 is common by 6.4 into NF1, number of cycles to failure for 1, which is 2.45 into 10 raised to 5 equal to so it's coming out to be here also the answer doesn't seem to be matching. So it's coming out to be equal to 9.57 into 10 raised to 4. Hmm. The correct answer is here also answer is not matching. Our answer was 9 into 10 raised to 4. Here it is 1.5 into 10 raised to 5. So it's bit off. Let's do one thing. Let's just recheck our calculations once, since there were lots of steps. So somewhere maybe we tripped. So let's try again. I'm just recalculating the values so that we can see still the same. Maybe if we do it more accurately, more number of significant digits, it will help. This is 245,168 into 10 raised to 5. Oh, okay. Interesting. Because we were just being lazy with the significant digits, I think that was the reason it was. So when I calculated again, I'm getting 1.49 into 10 raised to 5. So exactly matching with the answer.
Sir, audible?
Are you saying something? I could not hear.
Sir. Screen not sharing, sir.
Wait a minute. I think volume was low. What are you saying?
Screen not sharing. Screen
Its
not visible.
screen is not visible. Oh, okay, okay. Sorry. Your voice is very low. I could not hear. Sorry, I'll just share it now. Also, I'll put the solution in the online drive. So later, if required, you can see again. This is the one. Just checking why it was so off previously. Yeah, previously I had done some calculation mistake. So now it is coming fine. We can move to the next question. If there are any doubts, you can let me know. Hmm. Screen is still not visible? It's visible, no? Okay. So last question is cyclic softening in polymers occurs by which of the following? Here's the question. We have already discussed this in summarization that we have a dual mechanism of craze and shear band. So craze is um, Craze is also a form of a specific form of shear, and then you have bands of shear also. So they tend to form this kind of a shape as the crack moves. So you can also call this a epsilon kind of shape because you have these three segments here. The correct answer is D. So I think these are the craze. Yeah, you can see in the lectures for more detail on this. So this assignment is done. Let's look at assignment 0, which we'll solve now. Mhm. So this seems to be a short assignment only. If there are any doubts, you can let me know. Else we'll take a short break and come back to the assignment. Also in the discussion forum, there's nothing yet. But it's fine. Okay, let's take a 5 to 10 minute break, maybe 10-minute break, and we'll then start on assignment 0. By the time I'll also upload the things. Let's resume. The first question is the Poisson's ratio mu for isotropic material. You can guess if you know the answer, or if you feel you might know. So the first question is the Poisson's ratio mu for isotropic material in the plastic regime is. The correct answer will be 0.33. So what is the Poisson's ratio? Poisson's ratio tells you how much, if you apply a particular load, um, how much will your transverse strains be in your material. It gives you a ratio of the longitudinal to the transverse strain. So mu can be written as epsilon minus of epsilon 2 by epsilon 1 1. Oh, which of the wait, is this correct? Poisson's ratio of mu for isotropic material is, let me just check once. For isotropic materials, it will not be 0.33. For metals, it's usually around zero point 0.3, but for if it's the ideal isotropic material, it will be 0.5, because in I yeah, it is 0.5 for isotropic materials. So in one another way to validate this is, we know that for isotropic materials there is no volume change when you load the material, and volume change is epsilon 1 1 plus epsilon 1 2 2 2 plus epsilon 3 3, so which is equal to um, so this should be equal to 0. This is equal to volume change, and this should be equal to 0 if it's isotropic material. So the correct answer is 0.5. Question number 2. Which of the following statements is incorrect? Increasing the strain rate will decrease the flow stress of the material. In wire drawing, the strain rate is very high. So we do not have the solutions for this, I guess. We do not have solutions for this, but it is fine. Which of the following is incorrect? Increasing the strain rate will decrease the flow stress of the material. Mm, it's incorrect, yes, because it will increasing flow stress requires increasing strain rate uh, means that you need to apply higher stress so that your dislocations or other mechanisms involved can kick in to produce the strain that is required. So usually the stresses increase, like almost always the stresses increase if your strain rate increases, the flow stress. If you have doubts, you can let me know. In wire drawing, the strain rate is very high. This is true. Incorrect. In the necking region of the tensile specimen, the strain rate is very high. So in the necking region, locally the strain rate will be high because you are in the necking region or neck region of the specimen. Your cross section is reducing rapidly. The stresses are very high, and therefore the local strains are also very high. So locally strain rate is also very high. Materials with high strain rate sensitivity inhibit necking. High strain rate sensitivity inhibit necking. So high strain rate sensitivity will mean that if the strains are increasing or strain rate is increasing, the flow stresses also increase very rapidly. So in necking, we know that the strain rate is high. So, but if the sensitivity is high, that means the flow stresses will also increase rapidly, and that will cause some hardening and lead to a reduction in the, so that will lead to retardation of further necking, as a result of which you are more likely to get a more uniform deformation if your sensitivity is very high, because the neck region basically becomes very strong. So this is also true. The correct answer is A. How many independent slip systems are required to produce a general homogeneous strain in a crystal by slip? The correct answer, professor has taught, is 5. He has also um, explained, he has also given a proof for it, I think, of why the answer is 5, and this has to do with the strain tensor, I think. You need slip in 5, at least 5 directions to be able to, you need slip in 5 directions to be able to accommodate any kind of strain. So if you have 5, then any kind of strain can be accommodated. That's the logic. I think to the strain tensor, this can be proven. Here, engineer stress strain curve for SS316 is given. In question 4, it is asked what is the Young's modulus of the steel? Sigma 1, sigma 2, epsilon 1, epsilon 2 are given. So Young's modulus will basically be the slope of this curve initially in the initial region where it is linear, and you can write it as sigma 1 minus sigma 2 by epsilon 1 minus epsilon 2 equal to 50 by 0.00075. Let's calculate this. Let's calculate this and see. I think you don't have to submit week zero assignment, right? It's just for practice. Okay, this is also the same as the one of 2023. For the one in the current year, it's the same as 2020. Are you trying to say something? You are okay, fine. So let's calculate this value and see. This came out as 66.7 into 10 raised to 3 MPa. So it is 6.7 GPa. Sorry, 66.7 GPa is the Young's modulus. Now, corresponding true stress is for UTS of this and so UTS and epsilon are given at UTS and the true stress is asked. So we know the formula for conversion of engineering stress to true stress. It has been taught initially by professor. I think it was something like this: sigma equal to S into I think epsilon was equal to um, ln of 1 plus E. E is the engineering strain, and sigma equal to S into 1 plus E. I think this was the value. This was other way around. Yeah. Hmm. Is this correct? I'm just mentally trying to recalculate and see. Been long since I used this formula. Just check quickly. You can let me know if you know the correct formula. Else I'll just. Yeah, this one is correct. Yeah, I just recalculated, re-derived it. If you have any doubts, you can let me know. So corresponding true stress will be, if you follow this formula itself, I'll also put this also in the solutions. So if we go by the first formula, so sigma equal to S into 775.9 MPa, whose strain is epsilon equal to ln of ln of 1.135, which is 0.127. Whose strain is less than the engineering strain, uh, which is understandable, and true stress is more than the engineering stress. Okay. Question number 7. Arrange in the decreasing order of ductility. So this is interesting. Ductility is mostly dependent on plasticity, which can be deformed more easily and uniformly. So among these, it is known that gold is the most ductile. It's easy to make very fine laces out of gold. Then comes silver. I think this is the order. First one, silver, then copper, aluminium, iron. Because at room temperature, iron exists in BCC, so it is quite difficult to. So it has much less ductility compared to others. So this is, I think, very closely related to the uh, ease of drawing or ease of deformation, ease of metal forming or changing the shape of the material. So drawing is easiest for gold and most difficult for iron. Which among the following reduces fatigue resistance of steel? Polishing the surface, improves reducing surface residual stresses by short peening, carburizing, or increasing the grain size. Polishing will be good because surface flaws can reduce the fatigue life. Surface residual stresses by short peening are compressive, so they can help to close down any cracks which form, micro flaws which form. Carburizing the steel will make the surface harder, so surface flaw initiation will be difficult. So all of these are not the answer. Increasing grain size. So here we can see that if grain size is higher, then we know that the surface flaws formed by extrusion and intrusions, and these happen because your dislocations glide in certain glide and move through your material through certain mechanisms. We have seen what dislocation structures are involved, and they reach the surface. And if your grain size is higher, that is, there are less boundaries in your grain, it will be much more easier for dislocations to travel to the surface and form steps which can later on act as flaws. So increasing the grain size will lead to a reduction in fatigue resistance because of less obstacles, and it's easier for all the microstructure evolution such as vein, PSB, so cell formation to occur in the larger grain size material than in the smaller grain size material. So That is also one way of understanding this. Which among the following has the highest number of active slip systems at ambient temperature and pressure? Highest number of active slip systems. We know for BCC, it is about 48. FCC, it is around 12. HCP is, I think, 18. So among these, FCC has the most efficient slip systems, that which is why it is most ductile. But BCC has the highest number of active slip systems. So I think we can take BCC. With this, the week 0 assignment is also done. So if there are no doubts, we'll close the session. And this was the last session, last problem solving and out discussion session of this course. So thank you all for attending. I hope it was beneficial. This has been a learning experience for me. I wish you the best for the exam. I hope you are preparing well and you are able to enjoy this learning process also while preparing. Practice well, that will help you understand the concepts better, engage with the concepts, and then giving the exam will also be easier. You will be more confident. So I'll suggest you practice well all the assignment questions which you have. If there are no doubts, then we'll finish it now. Thank you. Goodbye. Oh, goodbye.